Welcome to Chapter 15 of Map Use. So today we are going to check out the spatial feature analysis. So knowing the geometric properties of a feature such as its area, volume, perimeter, center, and shape can help you to characterize it, compare it to other features, understand its relation to other features, and gauge over time. In this chapter, we look at different types of spatial feature analysis on the basis of geometric properties of features. Many of the methods in this chapter are popular with landscape ecologists or ecologists that study composition, structure, and function of a landscape. An example of this are patches in a habitat. Habitat patches make up a landscape and is one of the most important features that determine species richness. A patch is a small area of land that differs from the surrounding area. The area of size of an ecological patch or shape of the patch influences the diversity and the abundance of the species that live there. In this chapter, we will evaluate or show you how you can use analysis tools to identify, examine, and characterize individual features in a landscape. The properties and distribution of these features make up the landscape mosaic. So spatial feature analysis can be used to estimate the size of your features in your environment and numerically examine the area of a 2D feature. So how would this prove valuable in assessing property taxes? So let's take this image into account. This is a stone monument with a brass plaque in central Kansas. Well, that is insignificant, right? Well, not exactly. This monument was installed in 1940 before Alaska and Hawaii became states. At the time, the plaque was the geographic center of the United States. So imagine measuring the latitude and longitude of the U.S. This point in Kansas was the exact center. Well, until Alaska and Hawaii happened. Now the geographic center is in Belfour, South Dakota. So we are easily able to measure the central point in the United States. But what if the object is not 2D? Now it's much more difficult. So let's start with volume. You can numerically measure the volume of an object if you have its depth or height in area. Why is that important? So as a civil engineer, it is important to know the volume of earth to remove for a construction project. Volume isn't the only measurement, though. You can also measure based on the center, just like our example of measuring the center of the U.S. The center of a feature is called the centroid. Centroids are usually representative samples of a feature. So let's think of it this way with trees. The trees at the center of the forest may best represent the entire forest. So measuring the shape of an area is also very important. Shape analysis is useful in studying the effects of urban development, measuring the characteristics of drainage basins, and examining the patterns of geologic formations. This analysis is very important in legislative redistricting or evaluating the spatial compactness of a district. The original term gerrymandering was created in 1812 by Massachusetts Governor Elbridge Gerry, who, for political purposes, created a long, narrow, salamander-shaped district. You can also measure the perimeter of a feature to help characterize its edge. Edge is used in landscape analysis to assess the quality of habitat for edge-loving species such as deer or grouse. By calculating the perimeter of each land use class and then summing the values for each class, ecologists can determine important landscape characteristics, such as the amount of relative edge per class and the relative edge density. So when you measure an area, you are measuring the size of a two-dimensional figure or region. Using the area measurement tool, you can get a rough estimate. However, the area calculation method is much more accurate. So there are several different methods to calculate area. This figure shows a grill cell counting method. It is the simplest and most common technique for computing area in a visual way. You don't even really need to have access to a GIS to determine the area. So you can place your map into your grid cells on a paper. You can also use a GIS and evaluate the raster cells or an image processing software such as Adobe Photoshop. To determine area in this figure, you would tally the number of cells that fall into the lake and the cells that fall partially in the lake. You can then divide the number of partial cells by 2 and add this value. Because they're not whole cells, you only give them partial weight in your calculation. The next step is to multiply your water calculation by the ground area covered by each cell. How do you know the ground area of each cell? Well, let's check out page 377 under Grid Cell Counting. Easy. Let's say your cell is 0.1 by 0.1 inches, and we have 86.5 cells. So this is 86.5 cells times 0.1 in square inch per cell, or 0.865 square inches. The 0.865 inches is known as your representative fraction. To convert the map area to ground area, you then multiply the representative fraction, the 0.865, by your scale of the map. So let's use the scale of 1/2400. So 0.865 times 2400 square is 498,240,000. Let's convert that to feet. A foot is 12 inches by 12 inches, or 144 square feet. So 4,098,240 divided by 144 is 3,460 square feet. You can convert this to acres by dividing by 43,560 square feet per acre. So this would equal 79.3 acres. So as you can see, this can be done on paper with a little bit of math calculations. I don't know about you, but I'm sure I'd lose at least one decimal point or comma in all those conversions though. Image processing software can also be used for area computation by grid cell counting. Because each pixel in the scanned map image is a grid cell, you can count the number of cells within that area. To find out how much map area is covered by a single pixel, multiply that area by the number of pixels in the area and convert the map to ground area, just as we did with the other example. So in this figure, there were around 30,220 unique color pink pixels. If we knew that 84 pixels had a ground area of 300 meters, we could cross multiply to show that 1 pixel equals 3.57 meters on one side, or 3.57 meters squared, which is 12.75. This type of measurement is known as unit area volume of the ground area per dot. You'll see how this method is easier than the grid count method, but it still requires a good bit of math conversions. Using a GIS, grid cell counting is even easier. You would rather use a raster to calculate. Remember, a raster is contrasted with a vector. A vector used a point, line, or polygon on a map, whereas a raster uses pixels to show continuous data. So this is made even easier using a raster that is classed into categories, such as a satellite image classed for land cover. To find the area of each land cover category, count the number of cells in each classification and multiply by the ground area, just like the first two calculation methods. The quickest way to do this is to use the GIS that has the cell size as a property of the data. This figure shows the land classification data for Crater Lake, Oregon. The data in this sample is from the National Land Cover Database, or NLCD, and it uses the U.S. Geological Surveys with Landsat satellites at a 30-meter resolution. So this is standard for the United States. In this data set, each grid cell value is for a different classification. For example, Class 11 is open water. ArcGIS classifies the number of cells area, perimeter, and the centroid for you. The downfall of this method is that it's all or nothing. In the example of water, if the cell has any water in it, it is classified as a water cell. So the partial cell calculations are not possible. So the size of your grid cell can also determine the accuracy of your cell. Notice with the higher grid cell size, you also have a higher measurement of error. So here we are looking at a polar planimeter. So a polar planimeter is a tool that is used to calculate the area within a particular cell. This is a digital planimeter which functions very much the same. Let's look at some of these centroids for some of the basic shapes that we use every day. So remember, the centroid would be the exact center of that shape. So here's the exact center of a square, the exact center of that rectangle, and also of the right triangle. In this image, you are also looking at the centroid. So the centroid is the exact location of the cell. So it's within that rectangle. This is plus sign, right where my mouse is the centroid. It's the exact center cell. The same thing if you were looking at the different lakes. So although you may not think them to be the center of the lake, due to the amount of area within that shape, like Lake Superior, that would be the exact center. Although you may have thought the center to be more around where the eye is in Superior. Here you're looking at how this can be used as far as calculating the area in the center. So in this example, you are looking at a surface elevation profile. These are commonly used in construction. And you can see where a cut is made to level out this profile when you're making roads. So you can see how much cut off the top of the hill has to be made and where the different areas are that have to be filled in order to make a straighter profile. So this particular map is looking at contours, and you can see the centroid on the contour of this one is going to be approximately at the peak of this hill. And I know this is a hill because it is increasing in the closeness of the elevation or of those ISO lines, these lines here on a topographic map, as we increase in elevation. So you've seen several different uses for counting cells and centroids in this chapter. This concludes Chapter 15.